research that I did with Dr. Torelli at Merrimack College, and we investigated cyclodextrin complex Equilibria using excitation emission matrix, fluorescence, and PARAFAC. So to get started, we were interested in cyclodextrins as a molecule because when they are paired with fluorophores, they exhibit intriguing host-guest interactions that can be used for useful applications such as drug delivery once we understand them a little bit better. So the usefulness of the cyclodextrins comes from their physical structure, and you can see below that this is the beta cyclodextrin, and this is the alpha cyclodextrin. These are just multiple size variations of the cyclodextrin molecule. There can be alpha, beta, and gamma, but we stuck to beta for this particular research project. So to get more into the method, so the complex that we made in our project was a mixture of beta cyclodextrin and fluorine. So we made the solutions and then we measured them using an EEM, excitation emission matrix, which is a three-dimensional spectrum that combines excitation and emission wavelengths in conjunction with the intensity of fluorescence. So a sample would be excited at different wavelengths and measured over a range of emission wavelengths for each excitation wavelength. And you can see right here, these are the particular settings that we used. So after taking the spectra, we analyzed the data on PARAFAC, which is an algorithm that you can use on MATLAB. So for a cyclodextrin and fluorine complex, the two resultant components that you would expect to see would probably be a free fluorine and the cyclodextrin fluorine complex. However, we observed a three-component model in our specific case. We think that it's a contaminant, but we're not sure. More research has to be done to get a specific identification on that. So to explain this chart a little bit more, the column heading number of iterations represents the amount of attempts that the algorithm went through before landing on a model that fits the data. The sum of squared residuals describes the data that couldn't fit inside the proposed model for the specified number of components. Therefore, lower values are preferable to see. The percent explained represents the percentage of data successfully explained by the model. The core consistency value is a diagnostic that assists with evaluation of the suitability of the model, but it's not to be relied on to the three-component model. Using the spectra, we suggest that component 1 describes the fluorine complex with beta cyclodextrin. The second component describes the free fluorine in the solution. Component 2 matches very well to the spectrum of free fluorine in water. The score value for the free fluorine should have the highest value for the sample with 0 molar beta cyclodextrin. The sample should also have a score value of 0 for the 1-to-1 complex fluorine component since there is no beta cyclodextrin present. As the concentration of beta cyclodextrin increases, the score value for the free fluorine decreases and the score value for the 1-to-1 complex fluorine component increases. Calculations, the below expression can be used in a plot of the score value of free fluorine against the score value of complex fluorine. So plotting the free fluorine score value against the complex fluorine allows you to calculate a sensitivity ratio from the slope of the linear regression of the data. So that's pictured right here. Another linear regression using the sensitivity factor ratio also allows us to calculate the equilibrium constant. For our particular data from this experiment, we concluded that our beta cyclodextrin solution had an equilibrium constant of 945, and these results were comparable to previous trials. Further work needs to be done to figure out what that third component was in that data.